Now we have our next speaker as Alexander Barth. He is Associate Professor at the Geohydrodynamics and Environment Research Group at the University of Liege. He obtained his PhD in 2004 at the University of Liege on data assimilation in nested ocean models. After his postdoc at the College of Marine Science of University of South Florida, he worked on variational interpolation with DIVA and DIVA-END, and he is principal investigator of several European projects aiming to apply and improve these tools for generating climatologies based on in situ observations. Recently, he also investigated the use of machine learning techniques with ocean remote sensing data. I welcome Alexander Barth.
Okay, great. So thank you so much for having me here. I guess I will slide ahead. So thank you so much for having me here. I will speak today about generative deep learning for inverse problems in the ocean. And in the second part of my talk, I will also speak over more infrastructure packages to handling dates. So I'm really happy to come just after Andre, or not directly after Andre, but he set the stage really well for the question about inverse problems in the ocean, and particularly with generative AI methods. And so generally, like him, we are describing the state of a system with a large dimensional vector, x. So x can be, for example, the temperature, velocity of the ocean defined over a certain grid, but it can be quite generally also maybe just an image where you have a matrix of red, green, blue values. And for a geophysical problem, our state is often not completely known. Okay, so we have to live with this kind of uncertainty. And our knowledge and lack of knowledge is fully described by underlying PDF, probability distribution functions. Okay, but this PDF we don't have directly access to. And so the idea in many of these generative AI tasks is, can we learn this probability distribution function based on data? Okay, and this is, in a nutshell, the basic approach of the basic idea of several generative AI methods, like generative adversarial networks, diffusion model, or flow matching models. Okay. And specifically, flow matching is learns a mapping between a complex data distribution and a simple distribution, which is often a Gaussian. And it's actually quite similar to diffusion models, but it's unlike diffusion model, which using the diffusion process. The flow matching uses the advection process. And as an oceanographer, and I find it quite interesting that these two state-of-the-art techniques for generative AI use actually processes from fluid dynamics to learn really complex data distributions. Okay, so generally the function is nonlinear because we are mapping from a really complex distribution to a Gaussian distribution. And this mapping function is also called flow, and it must be invertible. So you have to go from a data distribution to the simple distribution and backwards. Okay. And we don't do it in one step, but we're doing it iteratively multiple steps. So that's also similar to diffusion models. You have a complex problem going from these two data distribution that you break down in a lot of simpler problems by doing via intermediate steps. And this mapping function is implemented by neural networks. But as we know, In general, neural networks are not invertible. You cannot compute the inverse of a neural network. And so the idea is that you use the advection process. So the neural network provides the velocity in which you would need to move in this high-dimensional state space. So X is a state space, typically high-dimensional, and you're moving in this space by a velocity which is prescribed by a neural network. And as oceanographer, this is very obvious. If you know where some object in the ocean goes forward in time, you can, by flipping the sign of the velocity, also go backwards in time. Okay, so the inverse comes really kind of for free by just flipping the sign of the velocity. And yeah, so that's the basic, that's the essential idea, how we can create an invertible function based on the neural network. And so the conditional normalizing flow was introduced by Lippmann in 2023, and they provide a tractable way to learn this kind of model, to train this kind of models, and just have a look at this picture to explain how it works. So you have your complex data distribution on the left and your simple normal distribution on the right, and you want to create a mapping between complex and simple. Okay. And you start with one sample of your data distribution, really chosen at random. And then you pair it with a sample of your normal distribution, equally chosen at random. Okay? And then you're simply saying, okay, my flow should be more or less a straight line. You pick a random point at this straight line, because we have to know also the flow at intermediate step. And you're saying that if I would be at the position x prime, my velocity should be pointing towards x0. Okay? So, and this is essentially the training objective of a conditional normalizing flow model. And when I first learned about this technique, I found it really surprising that it actually worked, because how do you know that x0 is the right pair that you should attribute to x1? Okay? How do you know that x1 should go to x0? And in fact, you don't know it. You don't know it. But you pick the point at random, and in the end, high probability regions from your data distribution will converge to high probability distribution, high probability region in your normal distribution, in your simple distribution. Okay, so the training objective, you will never run the cost function of your training loss to zero, but the optimal state of the flow will give you the optimal mapping between the data distribution and the normal distribution. Okay. And you can really learn arbitrary PDFs. So here just you start with a random distribution of points, and then you have your flow on the right-hand side, which moves this point around, and you can really learn a mapping between any kind of functions and any Gaussian distribution. And it's inverse by just flipping the sign. Okay. So this allows us to create now samples which are coherent with our underlying training data. Okay. But now the next thing is that we want to do. We want to create some samples for which we have some a priori information. So think of if you have a generative model that creates images, if you want to have images of a dog, and then it will just create images. You want to steer the creation of images by a given prompt, for example. Okay, but in Oceanography we don't have prompts. We just have saying, okay, I want to create an image based on some observation that I had at discrete locations. So the observation that we have are kind of the equivalent of the prompts in image generation. And actually, this is a solved problem, I would say, from the mathematical point of view, because we have the bias formula. Okay, the bias formula gives us exactly what the posterior PDF should be, given an uncertain state and potentially some uncertain observations. How do I combine a state with observations? This is actually exactly solved by the bias formula. And so we checked with a 0D case that indeed the flow matching models, when it is conditioned by an observations, potentially with noise, it gives us the right posterior PDF that what you would expect by the bias theory. Okay, and then we tried to we applied the neural network also to some data from CMEMS. So that's a subset of the multi-tenancy model here. That's here is the Liguriency. So we trained on 34 years of data. We used 1 year for validation, where we tuned the configuration of the unit, the number of layers, the number of channels, and so on. And the last year is for testing, and all I show here is the results for testing. Oops. So you have some temperature and salinity. That's the data that extract. You have some observation at a discrete location. And then we are running the flow matching models, and what you see here in the iteration is the advection time within the flow matching model, and which takes into account the observation to create a field which is coherent with the observations. And also, we are not only reconstructing the variable which is observed, temperature, but also salinity. And we don't have any observation salinity, so it needs to learn cross-variable correlation, as you have also seen this morning with Andre. Okay. And similar to a diffusion model, you get not a single estimate, but various estimate for the same observations. Okay. And then when you have a statistics, you can use also compute the mean, and 100 ensemble members seems to be a good choice, which I will use also here. And of course, the mean is much smoother than every single estimate, and that's really by design, because you don't have information at every single filament, at every small scales, if you have only a sparse observational network. And just as if you would learn a classical neural network in a supervised way, sparse observation, full field from a model, you would only have access to some kind of this smooth representation. But with generative method, you can also actually give a realistic estimation of small scales. So one of the techniques which is quite often used in this context is called the ensemble transform Kalman filter. And we just using the update step of this ensemble transform Kalman filter, which is often called also ensemble OI. And that's our baseline with which we compared our technique. So, and we have seen that for the validation test data set, we are providing better results than this ensemble OI methods when it's set up in a similar way. So the ensemble OI has also access to the training data set, and it's actually used to represent its underlying error covariance matrix. But one crucial aspect of most Kalman filter-based techniques, or indeed almost all used in operationally, is that they're using the assumption that the data set is Gaussian distributed. Okay, so that when updating the information, you can use linear relationships, and this is something that this is a quite strong assumption that we can get away with by using neural networks. And now we get an ensemble. Is this ensemble any good? And we can, in the context of probabilistic weather forecasting, there are several scores that have been introduced. One is the continuous rank probability score that can also help you to assess whether your ensemble is actually statistically reliable. And so that's the reliability column. Small values are good for reliability, and we've seen that indeed we had a lot of improvement relative to the ensemble Y technique. And another way is looking at talogram diagrams, where the talogram diagram should be flat, and indeed the continuous flow matching also improved relative to optimal interpolation. Okay. I will now switch to another part of my talk, which is more about an infrastructure package. If you have any burning question about flow matching, I can take it now. Yeah?
Just the relation between the velocity and phi, v and phi. I didn't understand the step.
Phi.
Yeah.
So
I think
phi,
you heard me, right? The
phi,
relation between v and phi.
Yeah. So phi is the function that maps between the simple distribution to the data distribution, yeah, and v is how you should move it at every time step. So the relationship mathematically is this. Is this advection equation? Okay. So it's more easily to understood as every sample that you're just moving it. Okay. And phi tells you how to transform the. So phi is kind of the integrated velocity. Okay.
Yeah, I was wondering if you saw any of the work that we did on the hard constraints flow matching methods, and whether you looked into these at all for this kind of application, because it seems like you might have some hard constraints in this kind of problem that you might want to be imposing in this case. I don't know if you'd have like a non-compressibility or something in your fluids, but I'd be curious to see whether there's an application there for that.
I have to say I'm not aware about this work, but I will be glad to learn about it. But the way that we implemented the observations, it's actually what we call a weak constraint, in the sense that observations themselves also have errors. But at a larger scale, in the larger picture, of course, there are hard constraints in the ocean, like you want to still conserve mass, or you want to conserve change in mass only within certain bounds. Yeah, that's certainly useful to apply when you go now to a full ocean model and to try to restart it, which is something that we want to do definitely.
Yes, I'm just here like wondering what could be like some physical interpretation of the probabilities, because when you measure, obviously you're going to be capturing the oscillation effect. But then when you go to the probabilities, what's actually going on? Because one way you can have, let's say, the mean flow, or perhaps you could have the flow which is undisturbed by the perturbation, so which are not exactly the same, even though they can be quite similar. But strictly speaking, they're not the same. So I'm just wondering what could be this probability. And I think you mentioned that the Gaussian distribution is one way to do it, but then you mentioned also there are other ways to do. So also how this interpretation could change upon the probability that you use.
So the physical interpretation is as, for example, the Gulf Stream. Yeah, you have the Gulf Stream flowing one kind of path most of the time, and sometimes the path is shifted. Yeah, so you have the Gulf Stream, which has two different states going from one to another, and the probability function will tell you what is the probability to be in one or the other state. And if you're using traditional method which only looks at the Gaussian distribution, they will give you a mean path. Yeah, and the mean path is maybe something which is quite unrealistic physically. Okay, because there's either one or the other state, but the mean is actually might have a lower probability. So think of it if you have a distribution with multiple peaks, multiple modes. Okay.
Okay, that makes more sense because yes, if you have like one direction and the other one, and if you think about a very simple state, it could be like zero.
Yeah, exactly, exactly.
The mean.
Yeah,
So yeah, very interesting. Thank you.
Yeah, thanks again for once again a great talk. I'm wondering about kind of high-dimensional application. So let's say that I have a kind of observing system that gives me 1,000 variables that are going to be collocated in space and in time, and I have collections of those. So I don't see why this would not be applicable to this. I'm wondering if there is anything that would get in the way to making advection like this 1,000 dimensional thing. And then the corollary would be, how do you handle the correlation and the cross, the probability being graded between variables, dimensions?
So yeah, exactly. So the flow matching technique, like also diffusion, they are really made for large, high-dimensional system. So that's really nice, and that's a property that we have also with a lot of ocean variables. So they don't. So they should also work with high-dimensional state vectors. And how now the relationship between different variables come from, and this comes actually from the flow. So the velocity that it's in this high-dimensional space, that's learned by the neural network. So it's kind of, if I go back to this image, it kind of knows that some variables, it kind of learns that some variables are not really independent, but they are related in pushing the state towards this region, which are known from the training data set. Okay, I propose that I switch now to the more infrastructure work about the handling times. So there is this climate and forecast convention about metadata for Earth data. And one aspect that I interact quite often with is how time instances are encoded. And if you work with netCDF data or also with SAR data, you always have seen that time are actually represented at seconds since the starting date, for example. Okay, and the CF convention defines this kind of format and also several calendars. And before, in Julia, so in Julia we have already quite nice packages for handling times, and they use internally a 64-bit integer counting milliseconds since the starting time. That's for daytime. Okay, and when I first was exposed to Julia, I thought this is actually a great compromise. So 64-bit integer with millisecond accuracy, it's actually quite useful. That is a good compromise, an excellent compromise between resolution and dates that you can represent. And in CFTime, I initially use the same approach, but some users actually use much finer resolution. For example, nanoseconds. So I had one user asking for, well, actually several users, two users asked for resolution within nanoseconds. Okay, and not only the data was then at the resolution of nanosecond, but also the time origin. Okay, and for me as a physical oceanographer, I was asking, does it really make sense for oceanography or climate science to have the resolution at the nano precision levels? So if you are in a boat, when you deploy an instrument, the instrument often does not have any time information. So you're standing with your watch and taking note of the time. And does it really make sense to have something at the nano precision level, nanosecond precision level? But in fact, it is allowed by the climate forecast convention, and it's also possible within NumPy. Okay, and a lot of users use Python. So if NumPy allows for nanoseconds and even down to attoseconds, there will be a lot of pressure to also to allow to read this data with the same without any rounding. And also there's a Python CFTime packages, which allows up to microsecond precision. So even also higher than our milliseconds. And also X-array and pandas default to nanoseconds. Yeah, and so essentially this was, there were some good reasons also to support nanoseconds for the CFTime packages. But one of the problem in NumPy, you have even attoseconds precision, but only with a fixed time origin, which is the 1st January 97. Okay, so if you're going down to attoseconds, you can only representing plus or minus 9 seconds around this time origin without overflowing the 64-bit integer. So it doesn't really make sense to allow this high time resolution without also allowing a flexible time origin, in my opinion. So that was actually the approach that we use in CFTime, in the new version of CFTime. And in fact, internally, we first define a duration, a time period. The duration itself is just a number, but all of this information that we need to interpret this number are type parameters. So in these type parameters, you see a factor and an exponent. So a little bit like floating point numbers, the duration still need to be multiplied by a certain factor and certain exponent in order to compute the actual duration in seconds. Okay. And with this, you can use as a resolution day, for example, and using then the number of seconds within a day within a factor, or you can also by having higher exponent higher than 0 to have smaller divisions, and you can go down to attoseconds if you like. And also the time itself, the duration itself, is also parametric, and it can be an integer 64 or a higher precision integer if you want. And for the duration, similarly, the duration is now also uses the origin as a parametric type. So if you have a large array where every element would have the same time origin, the same time resolution, then this information would only be stored in the type, and it's really very space efficient as well. And the compiler, if you're comparing two different time instances, which most of the time will have the same time resolution and time origin, the compiler sees exactly and can just make a subtraction between two numbers without making any conversion. So I think this type specialization of Julia played out quite nicely in this case. And then we can convert dates, times expressed in Julia with date or date time without any loss of precision. Also, we're handling all the cases that can be represented by NumPy's datetime64 object, and also Python CFTime, where the precision is down to microseconds. And also R, which is quite interesting. It uses actually a double precision floating point number to express the duration. Since a given timestamp, this can also be expressed in our case without loss of precision. And we did some benchmarked, and it's we will see that we were 100 times faster than the Python CFTime, but that's because the Python CFTime package only implements an object for the scalar datetime, but does not implement a type for an array. So that's the main reason why we are so much faster than Python. And you can also experimentally so there's also experimental support for GPUs. It works on AMD GPU, unfortunately not for CUDA right now, where you can run this code as well. So all of this annotation, type annotation, the compiler is quite capable of abstracting them away. Okay, so in conclusion, I talked in the first part of my talk about the flow matching model that generated some where you can generate some states guided by noise observations, and it's coherent with the Bayes theorem for a simple case that I tested. And we are showing quite competitive RMS errors and CRPS, continuous rank probability score metrics, when comparing to a update scheme from the ensemble transform Kalman filter. So it's essentially an ensemble Y. And for the CFTime, I used some, I made some improvement that it makes it much more flexible and to handle different time instances. And just for fun, so last year I presented to you how to compile Julia to WebAssembly to run some ocean models, some really simple ocean models, 2D, 1D ocean models in your web browser by using WebAssembly and the Julia source code. And quite interestingly, so we used GPU compiler for this. You can also run Julia on these really small devices, which are called ESP32. These are really widespread devices that you most quite likely have at home in some smart appliances. And interestingly, they're using the RISC-V instruction set, which is an open instruction set. And LLVM has a quite mature backend for RISC-V, unfortunately not enabled, so you have to enable it yourself. And then you can start to cross-compile Julia code to run on these small devices. Obviously, this you have only 4 megabytes of flash. You don't have space for the whole Julia runtime. And so you have to be things like allocations, things like this are a bit complicated, but you can cross-compile Julia code to these tiny devices. And here, if you are interested, here's this link how you can, for example, run this LED strip on a ESP device. Thank you.
Just on this point, so one of the things that I'm involved with is folks that are deploying Argo floats, and some of them now have a kind of a Linux core on them. But this seems to me that this will enable putting Julia applications on much kind of low power, low memory, like very tiny ocean observation device, right?
Yeah, exactly. So if it's a Linux computer, it's more similar to a Raspberry Pi, which is in fact a full computer, and you can run the complete Julia binary on a Raspberry Pi. That's relatively easy to do, or relatively straightforward. But these devices are much smaller, and actually they don't have Linux. They have a kind of that's FreeRTOS, which is running here. That's a real-time operating system, so a really specialized operating system for this case. So it's a really extremely constrained device, and you see it has only 4 megabytes of storage, and you have to also include the OS within this 4 megabytes. So it's really constrained environment. But typically, these are programmed in C or nowadays also in Rust. But maybe if this takes off, we can also use some nicer language like Julia to run on it.
Thank you. During the part on the CFTime, you also mentioned the satellite and the satellite orbiting at 10 meters per second. Often I encounter data that's stored as seconds and some timestamp, but not UTC seconds, actual seconds. Is there also a way to account for leap seconds in this, or is it still something I would have to do manually on the side?
That's a great question. So I have been in talk with some people from CF convention to better understand how the leap second is handled, because in the latest version of the standard there are actually 2 new calendars that have been introduced. One to precisely taking this problem into account, the leap second issue, but unfortunately they are not yet supported by CFTime. But it's certainly something that's in scope and that I would like to do. But but unfortunately, right now it's not supported. And also, it's not that clear to me how to convert. So in CFTime or in NetCDF, I like to convert directly to the Julia datetime, which most people are aware, which most people like to use. And this time object is not actually leap time aware, leap time seconds aware. So I don't know if this conversion can be made. If I have some data set which tells you, now I use leap times or no, I don't use leap times, can I convert them as they are now to the Julia datetime, which is leap seconds unaware? So it's not clear what should be the default behavior there for me.
Yeah, it's just maybe a slightly related question. Is there a CF convention checker in Julia? Do we have if I give you a netcdf file, can you check that it respects the CF convention in general?
Not in Julia. I'm not aware that there's a convention checker in Julia. There are some in Python and there are also some online services. Yeah. But I'm not aware that we have a CF convention checker in Julia.
Okay, maybe something to think about.